have to run the furnace to get this shit. So this is some sleep, some hours of experience, and the weather in the city is not good. It's not a beauty. It's not a beauty. Thus, we have such nice equipped classroom stuff. We have air conditioner, we have the lamps, and we have projector. So when you are in the room, so when you put down, let's try to continue our remaining. We have 6 hours remaining, right? Because tomorrow, actually, it's national holiday. National holiday. Actually, it's Dragon Boat Festival in China. I do think you have already seen. And next week, we will have 2 more lectures on Thursday and Friday. And right after, actually 2 weeks from that, we will have our examination on 2nd of July. So keep fresh and try to make your notes. Okay. Let's continue with our previous topic. Actually, I am always thinking that I am a teacher, right? Okay. It seems that a lot of stuff are going on in your mind. What I'm thinking about, you are not following my talking. So 1, 2, 3, get your attention, please. Okay. Am I a teacher? Yes. Am I a researcher? Yes. Am I an engineer? Yes. No. Yes, no. Actually, I treasure the title as a teacher most. But I am also a researcher. But originally, I want to be an engineer. When I was an undergraduate student. But after my graduation, because of some other reasons, I picked up my PhD and I picked up Pertemuan in university. Otherwise, I want to be an engineer. So some of you, the majority of you, will be engineer in the future. So if we are an engineer, we want to process our corporate concentrate and we want to produce blister. We will always have the idea that we should try to minimize the flow sheet. If it's in one unit, in one furnace, that's going to be perfect. And if we can make that, you will make great contribution. And you will really realize your probably career dream or some other dreams. So in copper, so when we are having concentrate and we are producing blister, so this part, we are starting from, we are knowing there is a star in the initial, so we are talking about the representative, it was carbon, right? Yes. And we are moving towards, so this is A, is there right? And I have this one, it's okay, I have this one. Okay, so we have the initial point as carbon, and we have point A, and and we have the point B, right? And we have point C, and we have point D. And after that, I told you that we should try to do some reduction. And for this one, we are having it as oxygen potential, right? And for the exercise, we are putting PS2. So actually, this is what we are doing. And for one section, 2, 3, 4. Actually, we have different sections. And from the initial start to point B, and we are knowing. So this is our. Actually, we are putting here. So this is melting. And all you are doing this very well. And if we are moving from B to C, so this is conversion. So this should be very solid in your mind. And from C to probably the terminal, actually, this is the range. And we are calling it refining. And now we are talking about the ideal of an engineer, we are stopping at this point. So this is blister production, right? Production. So from initial thermopyrite to blister, if we are making that in one furnace, so this is DB, direct blister copper. And if we are doing it classically, or we are doing it normally, so there will be two furnaces, right? There will be two furnaces, the smelting furnace and the converting furnace. So this is normal, classical units. And last week, we are knowing that this part is criteria. If you are having thermopyrite, you are moving to this side. But if you have some other concentrate, which is rich with actually CO2s, you can go directly to this direction. So this is DB. This is DB. And originally, there are actually 4 factories, 5 furnaces we are using this red line. And last week, we are knowing this. So this is what I am writing. So iron to copper ratio. So this is the difference between thermopyrite and CO2s. So we can do okay to good copper recovery or not. We will decide our technologies. And there are some plants or factories, smelters, like Dan, in Gologov, KSM. So they are using one direct blister copper smelting technologies. And in their slab, as I have been mentioning, so in their furnace, there are 2 layers in the furnace. The bottom layer is blister. This is fixed. So this is the name, direct to blister copper. So DB. B is blister at the bottom. And at the top layer, the slag. So only that, the slag you are checking. So iron, silicon, without calcium oxide, and big amount of copper. And if we are checking the other factories, smelters, they have iron, they have silicon, they have calcium. So 3 of them. So when we are having this one, actually I would like to see slag is not uniform. So it should be designed individually or on purpose. It should be designed. So every single copper mine, this should have their own slag type. But if we are moving to the classical, starting from thermopyrite, so we are doing the smelting with pyrite. So this is a solid conclusion. And if we are moving to converting, so we have 2 options. So we can either go for pyrite, we can also go for iron silicate. So we have 2 options for converting slag. So if we are checking, okay, this is 1, actually 2 slag types, 1 types, and here actually we have more than, if we have 5 smelters, it should be larger than 5 different types. And if we are checking the copper content, when you are having blister, you are having copper rust. Okay, so this is the information I want to summarize with such a figure. You know, Japanese engineer is always a group of people which are getting reputations, getting respect. The Japanese engineer is someone we should admire, actually. So this is more than 60 years ago, when they are designing copper flow sheet, and they want to add concentrate directly, and they want to have blister. And this is actually last week we have made a very good discussion. So one more time, what is the biggest difference of these 3 furnaces? Oxidative state or gas phase. So we have different oxidative state in the furnaces, and because we have to follow this rule, so they are starting from normal, the classical or pyrite, concentrate. So they have two divided into different sections and try to get different B, C, C, different oxygen potentials. So in the first one, they are only producing copper matte. So it was at low oxidation state. But for this one, they need settling times, a little bit reductant. So it will go deeper or go smaller. Normally, the first furnace is here, second furnace is here, and third furnace is here. So they are making such a circulation, trying to ensure the recovery rate of copper. So this is something you cannot meet or you cannot achieve in one individual furnace. You have to make this kind of change. So the gas phase is homogeneous. So you are not doing that in one furnace. But physically, they have made this to be a reality. Concentrate adding blister production. And this is the fourth furnace. So they are going for the fire refining. So if I am asking one more question, how many, or is this is anode furnace, right? Anode furnace. Are they using a single anode furnace, or they should have more than one? How much anode furnace they should have? So the answer is here. 2. Why they are having 2 anode furnaces? They are not using one, they have 2. Because this is quite continuous flow sheet, right? So if they have 2 anode furnaces, this means the chute here for blister copper tapping. So they should have a roundabout. They should have divided into 2 routines, to 2 furnaces, right? So why they are making 2 instead of 1? Why? This one can be bigger. It can be very big anode furnace nowadays, doesn't matter. So why they are building 2 instead of 1? Sorry. Production. I want accurate concept of production. Sorry. Maintenance production. Actually, I haven't put the keyword I want here. Some discussion? Internally, please. So why they are building 2 anode furnaces instead of 1? Finish your act. Only one keyword. One keyword.
Some furnace, one furnace is raw.
Raw. Spare one. Spare one. No. No. Why? Why they are having 2 anode furnaces? This is the individual, single, doubled. Why?
You can check quality.
Quality. The standard of production should be quality. I mean, should be standard. There's no quality difference. Why? Yes, please.
Because the subsequent process is casting, so when we try to cast it, we need time to solidify. So if we continuously the flow is continuous, so it acts as a temporary storage.
Okay, good. Okay, I'm trying to summarize a little bit. The reason of having 2 sets of anode furnace is because of one keyword, continuous. Continuous. So all big process should run continuously. We shouldn't do any big project batch-wise. It will be very demanding. This one, adding something continuously working. So this is what we should seek for. And for this anode furnace, continuously, actually, I forgot his name, but he given 50% of the right answer, and another 50 has a right put in here. So in anode furnace, we are moving from C to this terminal. So there will be another change. So it will be from here. So let's try to make another thing. It will be somewhere. First, you go to here and go down. So there will be another shift of oxygen state. In one furnace, you can do that, but you should do it batch-basically. If you are in two furnaces, you can do continuously. But when we are having another furnace here, we are doing this kind of oxidation, reduction, batch-basically. So in the another furnace, first reduction for the 2 hours, and the reduction like in the following 6 hours. 6 hours, and after that was the answer given by Boyd. We are taking our melting blister of melting anode copper in its furnace and try to supply the melting copper to for the casting. So two purposes. So one, because of the technical problems, we have to make oxidation, and after that we have to make reduction. So there will be change of oxidation state or oxidation. So it should have at least two phases or two furnaces. So now we are choosing the two phases in one furnace. And another section is we need to store the blister or the anode for casting in one vessel. So this is after the casting. So we have the anode, and that's all. This is for power, and we have already covered on the blackboard. So this is power. If we are doing, so this is some calculation. So this is step 1. This is step 2. This is step 3. See left, see right. Okay? Step 3. And this is step 4 for the verifying oxidation. And this is step 5 for the verifying reduction. We will try to summarize. In copper making, we will have 1, 2, 3, 4, 5. 5 different stages. And these 5 stages have been divided into 3 furnaces. Classically, 1 furnace, 2nd furnace, and a 3rd furnace. Okay, so this is what I want to summarize first. And in the Subish has covered. Okay, let's try to fill this blanket. So in this multi-furnace, so 1, 2, 3, 4, 5. Which number should be put here? 1. Oh, this one? 1. Oh, this one? 2. 2 and 3. Very good. 2 and 3. 4 and 5. That's very good. So this is 1 or 2 furnaces, 2 and 3 in the converter, and 3 and 5 in the furnace. So this is what we are doing. Okay, so let's try to check if we are. So this is some detailed information I'm going to do. And for double flash, this is another technology. Also produce copper blister continuously. So we are checking the major equipment in the smelter. So this is FSF. Plus smelting furnace. And the second one, FCF. Plus converting. And we have the anode furnace. So same story. So if we are putting 1, 2, 3, 4, 5 into 3 furnaces, this is 1. So there is no EF furnace specifically. And the assembly is happening in a circular. So 1. And for this one, 2. 2, 2 and 3. We are getting this one. And for this one, 5. So one more time, we have doubled anode furnaces because they are running batch-wisely, different period of time. For the first half, oxidation. Second half, reduction. Okay, this is for double flash. And another, actually very interesting, one, do you have this slide? Yes. Yes or no? Yes. Okay, good. This is very new information. You cannot find another slide talking about this process. We are talking about Mitsubishi. We are talking about double flash. And this is 2 furnaces, 2-step process. So 2 BBF, bottom blowing furnaces. So bottom blowing actually is a round or the sulfide reactor. And the first furnace submerged and then smelting furnace. So it's smelting, right? And second furnace submerged, converting, refining. It's very interesting, right? What are they doing? One furnace, actually one type of furnace, the second type of furnace, and we are getting anode. So if we are checking previously, one type of furnace, the second type of furnace, third type of furnace. And for this one, 1, 2, 3, 4 furnaces. But if we are moving to this one, actually two types, and both of them are bottom blowing, BBF bottom blowing, and this is happening in China, and this is done in at least 2 smelters. One is in Dongying, in Shandong province. So I will recommend all of you, if you have time, to try to travel in China. We have so big land, and we have different sceneries, we have different culture, we have different food. So try to explore. And in Dongying, this is one. It should be where it is. Okay, let me check the name. Sure. But it doesn't matter. It should be in the following slide. So we have 2 types of furnaces, and very interestingly, they are combining, converting, and refining. So what does it mean? They are starting from point B and terminate on this one. So 2, 3, 4, 5 are in this furnace. So if they are oxidizing first, reducing secondary, so they have 2 phases in one furnace, or they should have 2 furnaces, right? Because the gas phase should be continuously controlled. So in this technology, they have chosen one furnace, but the furnace is processed or is running with 2 divided period of time. One is for oxidation, another one, remaining time for reduction. So converting and actually reduction. This is actually we have one line in Dongying Dongyuan, and they are building second one. And there's another smelter actually in Homa, where I was doing industrial tests together with some partners. So this is something we are doing in China, and this works very well, especially when you are processing some gold containing concentrate. So the copper content in this feed, can be as low as 13%. So when you are adding copper here, the concentrate, the copper content can be as low as 13%. So if you are doing this in the other technologies, that cannot be profitable. For this one, you can make money. Because this equipment is cheap. So there's no. So I will try to have more introduction in the following hour or now. So very simple reactor, very simple flow sheet, and you have qualified product. So that's something we invented. Actually, the first bottom blowing furnace is built up in Hunan province. like 200 kilometers from here in SKS, 3%. Okay, so this is two-step, and this is in the first furnace. What we are doing, the concentrate is producing matte. Producing matte, and you are checking the matte grade is 76, so very close to white metal. Very close to white metal, and this one has already changed the concept from the phase diagram drawn by Professor Yazawa. In Yazawa's phase diagram, 70 actually is a limitation. It's a limitation, the roof. And now we have broken the roof. We have arrived 76. Especially when you are having very low copper content, which means iron content will be very high. Yes? If this one drop, this one will increase. And you will have more serious problem of magnetite. So technical problems will come one by one. So you have to overcome all of them. So this is matte with very high matte grade and sulfur dioxide and iron containing slag. So what will be the slag type here? What is that? Violet. Very good. It's violet. We have no options. Only violet. Okay. For the second furnace, what are we doing? So yeah, doing some white metal. So white metal, Cu2s, right? Some white metal, actually very close to white metal, with oxygen. So we have blister, have slag, and this one has been reduced. So this one is actually what we are doing for this reaction. Is starting from point B, covering 2, 3, and 4. We have no sulfur content blister, D, and we are doing reductant for the last step. So 2 steps in one furnace. So this is for oxidation. This is for reducing. So it's not very difficult, right? So if you are knowing copper production should have 5 stages, you are making what? You are making love actually. Actually play tours for children. So you are combining them and try to check the possibility and try to solve technical problems. Okay, so this is SLC and SLCR. So this one works very well. Actually, one doctoral candidate graduated from my group, from my team. It is probably some 2 of the boys who know him. Dr. Cao Shuhen, actually he is working for this company very soon. I think within 2 weeks, he will be an engineer in this smelter. Actually, this is very promising technology. Okay. So if we have, this is also directed with the copper, 2 furnaces. We are starting from concentrate feeding here. We are getting, actually not only blister, we are getting anode copper. So much shorter, right? Much shorter. And for traditional or the real direct blister copper, concentrate blister. So this is one furnace. This is also unique. So if we are feeding those numbers into this furnace, what are they? If we are feeding those numbers 1, 2, 3, 4, 5, so which numbers should be filled here? 1, 2, and 3. Yes, good. 1, 2, 3. And we will have the assumption that the sulfur content in the blister should be high. Yes. Should be high. Try to keep a good recovery. And along with the reduction blister, this slag we can regard slag as a converted slag because it's in equilibrium with our blister. So in this slag, we have a big portion of copper loose in the slag. So the slag is reduced in an electrical furnace for reduction. So the copper will be reduced, and now the blister will be produced. So we are adding them into anode furnace, and we are producing anodes. So for direct blister copper, we have 1, 2 furnaces, and 3. So 3 types of furnace. But for this one, actually we have between 2 types of furnace. So this is the shortest one nowadays. Okay, so direct blister copper, and this is very famous picture. What is this? What is this? Yes. If you are stepping in a flash furnace and you are looking at the roof, this is a copper concentrate burner. This is the core part. This is the core part of the furnace. And this photo is by Davenport, very famous professor. And this is in Zambia. So we have different layers, the central oxygen, distribution air, and the solid materials with processing air. The different layers. This is the core part. And we will have some hours discussing about this, probably in the following hour. Okay. So this is what I want to talk with metal making, the principles. And now probably we are moving to the practice. We will try to cover this one in the following hour. So this one, have you got a slide?
Yes.
Okay. So this is the layout or the precision of our smelters. Actually, last 2 weeks from now, I was here for several days for the industrial test. So this is bottom blowing as I was introducing. So we have a center here, and you are knowing there's a big river here. What is this? Yellow river is here. So yellow river flows like this. So all our smelters are connected with yellow river. So very easy to realize. And how about this one? What's the river here? This is Yangtze River. So we have 2 big rivers which are connected to the open sea. So this is for transportation purpose. And besides this river, Yangtze River, Yellow River, and we have those smelters very close to the coast. And you are knowing we are importing a lot of copper concentrate. So the transportation is quite demanding. So we have to build up our smelters along the coast or along the big rivers. And for you, it's not a big issue. You have islands everywhere. And you have very cheap transportation nowadays. So this is the layout. And if you're checking the technologies, this is China or our country is a museum for smelting technologies. The oldest one here, actually, it should be ARPAC, flash furnace. And we have top blowing, ISA, and we have bottom blowing manifold. So we have different, almost all the smelters. So this is where I was talking about the first bottom blowing furnace. It's 200 kilometers from Changsha. This is where we are sitting now. This is Central South University, and this is the first. Actually, this is where I was doing my entrepreneurship like 15 years ago. Not 15, actually 17. 17 years ago. Actually, majority of my classmates were threatened and they changed their directions. Okay. But nowadays, everything is very, very different. So if you are visiting those smelters, it's just like it's white collar, right? Just like a white collar jobs. So you are doing everything in the controlling office. Okay, for the flash smelting technology, there's a layout. So this is equipment. So where's the furnace? This is the furnace, right? This is the furnace. Actually, very nice in its appearance. So this is the furnace. This is what I was having. So this is the most important part, the concentrated burner. In this furnace, we have no other feeding mouse. All materials are added from this concentrated burner. So you have no other options. Just like people, we have only one feeding, we have only one mouse. Everything we are eating or we are drinking from mouse. So the mouse is very, very important for people. And this concentrate is also more important. So in Chinese, we have all the sayings. Taking care of the mouse, you will be healthy and you will be safe. You will be safe. So this is concentrated burner, and this is the reaction shaft. You are knowing that. Circular uptake. And this is the furnace. But along or besides this furnace, we have the feeding facilities. So if we are adding something, so nowadays, when you are very paying a lot of attention to healthy, what you should do? You should eat right portion of protein, right portion of sugar, and right portion of some other nutrients. So you need to take care of the distributions. Here is saying, you should be careful with the ratios between different materials, and you should also pay attention to the feeding rate. It should be controlled. So this is something is done. It's done. And for this part, this is even bigger than the furnace, is it? Uptake, and after that, we get the boiler. EP, actually the precipitator for dust. And after that, it will be washed with some water, and the gas will be used for sulfuric acid production. Actually, I was asking my professor some 15 years ago, and I was very curious about the layout of this furnace. And I asked him why. So this is one direction. So from this probably west to east direction for this blast furnace. And for this piston head boiler and the EP is from the south to the north. There is 19 degrees change. And there's a change with the gas. So like we are having the gas. So the first we have to make such a change. I was asking if we can rotate a little bit. So the furnace is from west to east. The boiler and EP precipitator is also placed from the west to the east. Whether there will be any difference? Is this a question? Have you got it? We are not making such a triangle. We are making it parallel. It will be easier for the gas flow, right? So this is less dragging force. Everything will move massively. And I haven't got my answer actually. My professor was a little bit surprised with such a question. And his explanation or his introduction was that the first copper flux melting smelter was built in Hajavarta in Finland. Actually, it's a place Hajavarta. And the first blast furnace, because of the limitation of the house, this is not enough with the length, so they are making such a third. And this is the first, just like my example. When the first furnace is commercial, is used, is running properly, and when the second one, the third one, when they are building, they do not want to make any change. They just want to copy it. So all the copper smelter, they have such a layout. I have no idea whether will be any difference. We are changing it a little bit. It should be better in my mind, because nowadays, very seldom precipitation is happening here. Because the gas is high temperature, when we are entering the PVC boiler, the temperature will drop. And those melted droplets will precipitate on the surface. And we are just like What can we do that? Aging layers. And the loss will get smaller and smaller. So this is a big problem. And if we are changing a little bit, I do think it will help. I have no idea whether we have the opportunity in the future. We can find a furnace, a flat furnace, running directly, not with such a change. Okay, this is just a discussion or talking. I need the story with you. And my thinking is that always have some pure curiosities. When you are reading something, when you are getting some knowledge, getting some information, always be curious about that. You should think by yourself. Okay, and this is a history of flash smelting. So if we are reading 1949 or 1951 and 52, so this is very, obviously, very familiar years for us. But this is the first commissioning of blast furnace. This is in Hyderabad in Finland, small town. And this is why we have I have had my PhD study in Finland. So this is expansion very dramatically. And the first copper smelter is in China. It's 90. I'm trying to find it. Okay. It was in 1976. The first flash copper smelting furnace is built in China in 1976. And we are having that. And the first double flash is 1992. It's in Ellicott in USA. And in China, actually 2006. This is a very important year for Chinese copper industry. And after that, we are leading in this field. Okay, and this is a map. I photoed in the center of that because flash we always have the company's name. It was Autotech. And we have a scholarship in CSU. It's big amount of money. It's big money. So try to make 1 or 2 teams within the class. And I will be happy if I am invited to be the supervisor and try to join this competition. Autotech scholarship will be granted after competition. So you are having an idea, you are preparing materials, and you are making demonstrations. And they will have reference. And this is big money, at least for students. So try to get this information. And this is a very big company, or the biggest one actually. This is the biggest company for metallurgical technologies, equipment, and service. The biggest one. And this is actually when I was a student, I got this favor from their headquarters. So it was here. In Finland. So you are checking Autotech furnace in Asia, in North America, in Europe. And nowadays, we should have new ones here, and this is Pasa. In Philippines. Okay, this is very interesting. But I have been mentioning scholarship for CSG. Actually, this is a framework agreement. And actually, I am sitting here. This is my laptop. Actually, I'm a disposal. So it was more than 10 years ago. And this is the research center. Actually, this is my photo. Okay, 10 minutes break. We will come back. Talking? Seems like you are becoming more talkative. It's break. Okay, as I have been introducing, so we have been building very good, very close relationship with Autotech. This is an agreement we signed actually, as I have introduced 10 years ago. And we have scholarship on all that to try to negate the belt, because this one is an international award. It will be very helpful with the CV. Okay, so this is actually the meeting. This is CTO of AutoTech, Dr. Gayatri. And this is our former dean, Professor Chai. Actually, we are in the research center. Okay, this is what we are doing. And if we are having the introduction to the flash smelting furnace. So this is the core part. So this is the cross section. We have already got the burn view or over general view of the furnace. And now, if we are making the cross section of the furnace or the constant burner, so you are finding out that we have actually this is generation 6. When we were in the research center of AutoTech, we have checked there is one room which are designing this burner. So they have more than 10 generations. So actually they have different shapes, different ideas. So this is one which is the most widely used one. So this is actually we call it CFD. Actually we are checking. So this is powder, concentrate. So this is what we are writing here, the concentrate powder, and this is the processing air. Like 80% of oxygen, 20% of nitrogen. And we have the central oxygen pure one, distribution air. So 1, 2, 3, 4. So 4 different layers. So it's quite expensive one. And this is the burner. And we have been talking about the conditions or distribution behavior of arsenic in the copper smelting process. We are knowing that in this section or in this zone, and we are having the highest concentration of oxygen, right? And this should be the center of chemical reactions, oxidation reactions. And in this region, we have the highest temperature. So do you still memorize what is the temperature I introduced last week? I measured once, and I burned some money there. Actually, the number in my measurement, it's like 1470. It's more than that. And some other, not direct, that second-hand measurement, it was 2000 plus. So this is very intense reactions. Actually, we have to admire what those engineers were thinking. Beforehand, actually, if we are reading the powder with information, so let's try to start generally. The starting materials. So first of all, the powders. So it's minus 300 mass powder. So it's like 13 micrometers or 42 micrometers. So they are product from addressing. And the second important parameter here, the moisture content. So it was less than 0.3%. So let's try to have some other thinkings. If something is in very fine powder form, just like concentrate, and the powder contains almost no water. So what will happen? So if something is in powder form and it's very dry, what will you have in your mind? Or have you ever experienced something like this? Something is very dry and it's in powder form. Have you ever saw such a phenomenon? Sorry. Auto 9, okay, very good. Just like, this is one example, some other examples. The desert. Have you ever visited some desert? Yes or no? A lot of sand. Desert. Have you ever been there? Yes or no? Have you ever seen a dance by desert? Have you ever saw a dance with desert?
Yes.
When we have a big wind, the desert will move along with it. This is one example. Another one, if we have the rice powder or the wheat powder for cakes or for our dumplings for food. So those powders, they are transported with pipes. So they are ground in very fine powders and they are moved that. Actually, the general or the summary will be, if we are having very dry and very powder form materials, they can move just like water. Just like water, just like air. So they have such properties. So this is why I was telling that we should admire and we should pick up lessons from the engineers, from large engineers, because they have found out, okay, when this one is original form is fine powders, and when we are drying that, it can move like water. So this is super nice. And if you're still memorizing, I was giving some statement of hypochlorite powder or concentrate. We are telling it, so it should have 3 different functions. What are they? If we are talking about concentrate, it has 3 different functions. So first one is fade. It's fade, good. And second one? Second one is reductant. It's reductant. So we have 3 different functions. And if something is flowing like water, and it can be a fade, which means it can go to where we want. And secondly, along its movable, it can produce energy by itself. So this is something very genius idea. So this is one layout. And after that, I have another statement. And let's try to share together. So we are having like this reaction from the initial point to point B. In point B, we should have a stack. And what is more importantly, we should have another phase. It should be met, right? So we should have 2 different phases. And if we have 2 phases for metallurgists or for corporate metallurgists, we should have the mission. We should separate them. So if we are rethinking the furnaces for Metallurgy process, what is the function for the second furnace? What is it? In Metallurgy process, the second furnace is, sorry? EM furnace for settling. EM furnace for settling. So just like the first furnace that we are having from the initial point B, we would like to have the oxidation reactions happen intensively. So keyword will be intensively. And if we are having the matte droplets, if we are having the slag layer, so what should we have? We should have very, very peaceful environment for separation. The keyword will be peacefully. Peacefully, okay. 2 keywords: intensive oxidation reactions, peacefully separation. Separation. So if we are engineers, we are metallurgists, if we are designing some process where our chemical reactions are happening intensively, where our products are separating or are settling peacefully, we are at a win chance. We are winning the game. We are winning the game. So this is what we should have in our mind. When we are designing chemical reactions, it should go intensively. And if we are having the product, we should have very peaceful environment for separation. Okay. So this is what we are having for the flash smelting. And for the constant burner, as I have already introduced, because sulfides, minerals, it should have such a property. It can flow like water. So if we are checking, the center top is air, and all the solid materials, including our concentrate, flux, something else? Concentrate, flux, something else? Secondaries. So, for example, what can be the secondaries? Dust, very good. Some more? Dust, very good. Sorry. Recycled? Recycled product. Keep in mind one more time. If we are adding all the materials with such a constant burner, the solid materials should flow like water. If we are having such a requirement, the concentrate should be dried, and the water content is less than 0.3%. And for the flux, same story. It should be grounded into fine particles and add together with the concentrate. The dust is in fine form, fine powder form, it's okay. So for the other secondaries, it should be grounded in fine particles as well. So if we are naming two representative secondaries, first one can be dust, second one can be slag concentrate. You have already know that, right? So we have incorporated the slag, so we should recover them, and they are recovered in the form of slag concentrate. So this is solid materials passing channel, and for the rest, they are air for distribution and central oxygen and processing air with oxygen air. So this is what we are having. And this is a very well protected pattern, by Alltech. This is quite expensive, and the materials for this consumer burner is only stainless steel, 316L. It's very cheap with raw materials, but for this one, when it's in a shape of a consumer burner, the price will be increased by 200 times. So this is knowledge. Okay. So this is the development of the history. The Chinese companies, the different types. But that one we are introducing was the best one. And another very interesting idea. So what is this? Tornadoes. I don't think you have witnessed such tornado, but we have witnessed this one. We have probably have some videos, pictures, tornadoes. Okay, one more time. In this reaction, we want this oxidation reaction to go intensively. So my following question will be, if, pay attention please, if we want to have such an intensive reactions, what should be provided? Or what will be the basic conditions for intensive reactions?
Pressure.
What should we have?
Pressure.
Sorry. Pressure. Okay. It's yes and no. I need some explanations or some added information for pressure. So if we want to have intensive chemical reactions, what should we have? What should we have? You can have a million discussion in her. What should be provided? Okay. Okay, attention please. So now I want to have some answers from you. So if we want to produce, or if we want to have such intensive chemical reactions, what should we provide? Reactants. Very good. Very good. Some other information? Sorry. Catalysts. Very good. For chemical reactions. Very good. Very good. So graduate students should have such a behavior. So you should always think independently. Some other information or keywords? Reactants, catalytes. Something else? Energy. Good. or temperature profile. Something else?
Remove the
Remove what?
product. Remove the product.
Okay, to remove product. Okay, so the low concentration of product we are driving, we are pushing the directions. Sorry. High oxygen supply. Okay. Okay. Okay, let's try to summarize a little bit. This is the ideal one. One of the best chemical reactions we can have in metallurgy. So what are we having here? Temperature, highest. Reactants, oxygen, concentrate, flux. They are added continuously, right? And for the products, they are removed. They set down, right? So let's try to have some summary. So the temperature should be high, and our reactants should be very well mixed. Yes, this should be homogeneous. We should have reactants. If we have more than 2, they should be mixed properly. Mixed properly, and the product should be removed. I say fast, very fast. So if we are having such a condition, the chemical reaction can be the property or quality of the reaction can be guaranteed. So this is what this burner has produced. Everything is mixed very well, so they can be produced. But if we are reading from this figure, we are knowing this is distribution here. So the materials after injecting, it will be looks like an umbrella. If you are on an umbrella, so everything is moves like an umbrella. So this is the shape. So it looks good. And when we have such a shape, the dropping or the moving parts of the particles will be extended a little bit than the vertical one, right? A longer distance. And another story is from this one. Actually very big contribution by Chinese engineers and by our graduates. So if you are looking at this photo, this tornado, right? Tornado. And when we are talking about the conditions for ideal chemical reactions, everything will be around the tornado will be sucked in. And the air and some materials that mix very well, right? And all the materials are rotating and lifted up. So this is the idea. One of our graduates, actually for the one, is leading, but we have other graduates. So they are turning tornado the other way around. So this is a reaction shaft. This is the burner. If we are making a tornado inside the reaction shaft, what will happen? Which means all the copper concentrate will be sucked in, and the oxygen will be the meter. It will rotate. And if we are having umbrella shape, all the particles will react and drop. And for this one, the chemical particles will rotate and drop. So you'll have longer distance and very good homogeneity. That means the materials. So this reaction is very good. So this is the revised tornado shape concentrate burner. So this is popularly used nowadays. And we have sold this one to USA, I think 3 years ago. If we are reading the history, the first concentrate burner for glass converting furnace was in USA, and nowadays the Chinese, the burner is sold out to USA, and we have like 3 or 4 smelters which are using this one. So this is very nice. So this is application. This is our graduate. So this is the contract from Utah. This graduate. And this is conditional release. This is the release. Actually, if we are reading some story, this is Professor Joe. I think he is probably one of the leading experts in USA. Okay. And this is a layout. Actually, probably some of you know this is the burner. This is the burner. So we have, in the future, if you have some more experience or you have more opportunities, you will know that. Okay, some very important parameters for flash technologies. So first of all, you are knowing, or let's try to make summary together. If we are talking about flash smelting technologies, or if we are talking about flash technologies, or solid materials should be fine powders and dried particles. One more time. If we are talking about flash technologies, all solid materials should be fine particles and dried particles. Dry and fine powders. So they should be the criteria. So this is the requirement. Copper water content, moist content should be less than 3%. So if we are talking about concentrate, this is the product for flotation, right?
Yes.
So if you have still got the memory of the flotation shell or cell, the water content for the concentrate is always like 8 to 10%. We have water concentrate. So this water should be removed. So rotary grinds and steam dryers, they are used. And for flash technologies, oxygen-enriched air is used. So this is for the oxygen production. And previously, only air is used. And for flash technologies, we are using oxygen-enriched air because when we are producing oxygen, it's demanding. Any separation, probably we are also studying thermodynamics. So the entropy of the system is increasing all the time, right? So this is thermodynamics, entropy increase. But if you are separating nitrogen with oxygen from air, what do? You are decreasing the entropy. It's disorder system to order system, right? So you are decreasing that. So when you are decreasing the entropy of the system, you are paying something. So you are paying energy sometimes, or you are paying work. And for flash technologies, for accurate measurement of the charge of oxygen is very important. As we have been mentioning, the ideal mixing of air and solid feedings, they are very important in making such intensive chemical reactions. And met and slag separation, the settler is very peacefully. And if we are having some more discussions, sometimes when we are having unreacted, probably it was copper sulfide, and if we are probably this is one reaction, and another one is in copper smelting, and another one if we are having this one in sulfide form, and we have another one as copper oxide. Because this is chemical reaction, there will be some sequence for the particles. And iron, probably the particle size is larger, so it is a K or sulfides. And copper, the particle is smaller, so oxidized. So this is over-oxidized. And this reaction will happen. So we are knowing this one very well. So this is interpretation of iron sulfide will be oxidized preferably. And this reaction will happen, right? And this reaction will also happen sometimes. We are producing copper and sulfur dioxide. And when we are having this one, we are having bubbles in the settler. The peaceful separation of atmosphere will be destroyed. So we want the reaction happen in the reaction shaft. So met and slag separated in the settler and intermediate part. And met is for method for converting and copper recovery from slag, or from ear burners, or from rotation, And this is, very nice example. This is for Toyo copper smelter. It's from Japan. Toyo is the same thing. And if you are reading the flow sheet, we are knowing that. So the first important stuff for this flow sheet, we are looking at this one, right? So this is a blast furnace. And before this furnace, what are we having? We are having a very large facility in preparing the materials. So this is a flash furnace. We are producing the mat, we are producing the slag, so everything is here. So we are going to the converter, and we are going to anode. So there are 3 furnaces that we are describing on the blackboard as well. But for the raw materials, let's try to do it. So copper concentrate, store in house. Very carefully balanced, blending. So you cannot use single concentrate. You have to use multiple resources. So they should be blended. And also, there is something I want to point out. So his hickory, very famous, is a ore for silicon oxide. And for this hickory, this is the sand, just like the river, the beach of the river. We have the sand. But for this river, for this sand, they have very fine gold patterns. So the information inside, we have gold in a silicon. Is this popular? Have you ever saw such videos talking about how to separate the gold from the sand by gravity?
Yes.
Have you found that?
Yeah.
Because if you are shaking it,
Yes.
gold is heavier. It will settle, and the sand will be driven away by the water. So this is very classic, very traditional. But there is a criteria. The particle size of the gold should be coarse, should be big enough. Otherwise, you cannot get it. And for this one, SRA, they have gold, but the gold particles are very, very small, which means that physical separation is not important. It's not possible. So what are they using? So the Toyo copper smelter, they are holding this sand, and they are adding this sand a silicon flux. So with such a design, the gold will enter the matte phase. Silica will be in the slag phase. So they are enriching their gold. So this is very nice design. So we are producing copper together by capturing the gold. And this is a suggested technology in China, a suggested technology in the world. So when you are running a copper smelter, you are encouraged in using some precious metal-rich silica flux, especially when you're having gold. Okay, this is one example I want to share. And another one is about this one. We are having this, we have a steam dryer. So this is the photo. And the most widely used one is Kumra steam dryer. So Kumra, actually, this is a name of a person. He used to be a doctoral candidate in Helsinki University of Technology, where I was studying, Civil University. And after graduation, he entered Outback to be an employee. And right after the commissioning of flux technologies, and he realized that the pre-drying of the concentrate is very important. So he made this patent, and he inserted this patent for equipment. So this is how they are drying. The copper concentrate is passing through those space, or the channels. And for those pipes, what are they? Those pipes, they are steams, water vapors. So we are knowing that if we are having those concentrate in fine powder form and there's no water, but there will also be some risk. If we are moving the wet powder, the wet rice powder, if we are moving the cold powder, if we are moving the concentrate powder, so when they are very dry, there is a big possibility of risk exposures. When the temperature is not well monitored, when there is oxygen contained in the system, once there is a spark, or once there is sudden heat, there will be exposures. So drying such big quantities of concentrate to very dry and fine powders, this is a challenging job. If we are heating up this one in rotary climates, so the concentrate powders, they are burning. So once the concentrate is burning, the sulfur will be removed. So the phase assemblies will change, and we are not making the right metallurgical process. So the temperature here should be very nicely controlled, and those powders should be dried stepwise. We shouldn't push the temperature too high, and it should be dried averagely. So this is the correct part. And the second one, if there are large quantities of materials passing through those materials, which means there will be a lot of interactions between the pipes and solid materials. There will be corrosions, physical ones. So the materials here is also critical. So temperature is very critical, and the corrosion is very critical. And what's more, there are 8 to 10% of moisture in the concentrate. And when you are removing that in this dryer, the water content, vapor content in the space should be removed properly, and it will precipitate as water. So the separation of a water phase from such a system is another part. And this one is also rotating. So once in the future you have opportunity in the smelter, so try to stay very close to this one. This is a very nice designed equipment, and I do recommend you have some detailed study of this dryer. And another important element or component in the flash smelting or flash smelter is actually, if I am projecting this figure one more time, so if you are checking, they are iron or steel framework, and right behind this iron or steel framework, what are we having? We're having bricks. Try to keep the thermal. And right after, actually, if you are writing nicely over here, so this is the frame. So we are going over iron frame, and right after that, there will be brick. And after that, we are having some cooling element. And after that, we are having another brick. So several layers, and this is a layer which we are get contact with our slag, mat, or blister. And on the surface of here, we will have linings of slag. The slag will be cooled down on the surface, make a new layer. So the slag will not contact with the bricks. So what is more important? It will be the temperature in this bricks, right? So the temperature is well controlled. The line will be stable. So the dissolving, the forming, it will be dynamically constant. So actually, if this one is break, This is oxide, it will dissolve into the slab, and this is the water inside. So if water is linked to the melting phase, it's going to be another very serious accident. So the water cooling element is another important material. So the thermal conductivity and also the corrosion. So this is water in, water out, water in, water out. So this is one very big one. And I want to share with you another very interesting information. One of my master students, he graduated 2 years ago, and when he joined Jinchuan Copper, it's a very big, very leading copper smelter in China, and his first job, his mission, he got the mission job from his boss, and his most important responsibility was checking the temperature of those pipes. So if there is a big furnace, you cannot measure the temperature from the slab, from the mat. You are not measuring that because you have several layers. It's not possible to measure it. So what should we do? We should always follow in the temperature profile of the furnace. What should we do? We are measure the water. If some pipes, the temperature is keep increasing, what does it mean? What does it mean? It means there are corrosions or they are destroying this lining and the bricks. The distance is smaller. We are getting more energy or thermal from the furnace. So the water in this cooling element will increase dramatically. So this is very, very top level risks of accident. So this is something we should pay attention. So water cooling jacket. Okay, so we are knowing, okay, this is very important component, the burner, the steam dryer, and the water jacket. 3 important components in flash smelting furnaces. And if we are going back to the energy balance, so we are knowing that what will be this, any energy, the input energy, will mainly coming from the solid fate, which can be interpreted that when we are running the mass melting process, the energy is supplied by chemical reactions. And the chemical reactions is stored as in the copper concentrate. And sometimes when we are initiating or improving the conditions, we are adding some natural gas or some oils. So same story, when the sulfur is removed, there's no more oxidation reactions. The temperature in the settler and in the space of the settler, it will drop a little bit. If we want to improve a little bit, we should add some natural gas for the settler. So this is all the energy input, 100%. So if we are talking about the energy output side, the largest one will go for slag. So this is what I have already recommended you. If some of you, one of you, actually I should be in the group as well. If one of us can have such a pattern, can invent such a technology, we are recovered. Not 100% of the error in the map, in the slag, like 10%, 20% is going to be very, very big difference. Very, very big difference. So copper smelter is no longer producing copper. We are producing electricity as well. So this is, so far there's no feasible technologies. So far there's no feasible ones. In the future, I do want to have some cooperation, or I do want to have such innovations or very important contributions in the future. And besides this one, this is a solid loose. You cannot change it because slag is so important. So we are not changing the slag, the composition, no. Temperature, no. Then nothing can be changed. It's a big volume. And for the matte phase as well, the composition is fixed and temperature is fixed. So you are not changing it anymore. So only 2 parts. One is for the gas phase, one is heat loose. For the heat loose, So if we are using this water cooling jacket, cooling element, they are taking away some energy. And this part is for the purpose of protecting our furnace, right? So if we are having some weight loose, and we have this linings, the slag linings, so it will help us in protecting our furnace. And only one here is about the gas phase. If we are using less nitrogen, the gas will take less energy away, right? So the energy enrichment is a critical part. So in 1949, the first flat smelting furnace, they are using air and they are adding some nitrogen gas to try to produce some energy for the process. But right after 1970s, when the price of oil, the price of nitrogen gas increased dramatically, so they should find a solution. So they are replacing the air to be oxygen enriched ones. So after that, the furnace is autothermal. So because when we are using air, 21% of oxygen, right? 80% they are waste. They are only taking away energy. But if we are using oxygen enriched air, so they are taking much less energy from the furnace. So the furnace is 30%, it can be optimized. Optimized, please.
I have a question for mining. So
Yes.
in the smelting, iron smelting process, we use the type of lining. The mark is Strawberries. Do that type of lining can use in the copper smelter?
Sure. Actually, it's a very good question. Lining is a very important topic for all the furnaces. And the lining is not pre-designed or pre-constructed. The lining is dynamically formed. Composition of the lining is same with the slag. So when you have a slag, the slag will solidize, will precipitate on the wall. This is the composition of the lining. So the lining, the composition will depend on the slag composition. And it's dynamic, equilibrium. Okay, so this is something I want to share here. So the gas is how we are controlling the overall equilibrium. We have no other options. This is solid, right? Fixed. The input will be fixed. And for output, this is fixed. So this is the only freedom we can have. So we are changing the oxygen enrichment. As I have been mentioning, the boy graduated from my team, he worked in Jinchuan Corporate. They are using pure oxygen now. Pure oxygen, there will be a lot of beauties. So first of all, they are losing less energy. So they can produce, or they can add much more dust. Dust and oxides, they are not containing any energy, right? So this is one beauty or one advantage. And another is that when they are using pure oxygen, the arsenic will go more to the slag phase. We have been discussing about the arsenic behavior last week. So when we are having pure oxygen, like 60% of arsenic will go to the slag phase. It's going to be another beauty. But when you are using pure oxygen, the reaction here will be more intensively. So the challenges for the burner will be very, very different. So we should have another technical problems. Okay. So this is where we will end. And tomorrow we are having the national holidays, I have been mentioning. And we will come back next Thursday and try to print out all our slides and try to make some discussions, especially when those ones who are using laptops. You are not using laptop during examination. Okay? Okay, see you.
kan? Oh ya itu ya.